All right, so Foundations of Math 34.2, we're talking about permutations and factorial notation. So if you remember at the onset of this chapter, we talked about permutations and combinations are something that we're going to study this chapter. And permutations is the first thing that we're going to study. Factorial notation will come later. The first thing that we want to talk about are permutations. Okay, so if we think about this little example that you have in your book there, page 238, it says this: Naomi volunteers after school at a daycare in Whitehorse. Each afternoon around 4 p.m. she lines up her group of children at the fountain to get a drink of water. So the question is, how many different arrangements of children can Naomi create for the lineup for the water fountain if there are 6 children in her group? So this is the question that you're thinking about. You're thinking, well, we just learned 4.1 about fundamental counting principle, right? And the different variations of options that we have. So if we have 6 kids, you know that they could be rearranged in a whole bunch of ways, right? We could have, kid A followed by kid B, C, D, E, F. No problem. Then we could start switching them around, right? 1 at a time, and then 2 and 3, and so on. And if we were taking a look at the fundamental counting principle, we could solve that pretty easily, and we will in a second. But what I want to get at here is that the number of different arrangements, okay, the number of different arrangements is really what we call a permutation. So one of the options for the lineup is called a permutation. So let's just take a look at this definition here. Permutation. Flip that and bring her over into the notes. Make that a bit bigger for you. So a permutation is an arrangement. Okay, so you think about arranging things in a different order of, and this is kind of important because every object, if every object is different, okay, then you have a certain number of permutations. If you have 2 or more identical objects, that's going to affect things, but we'll talk about that later. So technically, it's an arrangement of different or distinguishable objects in a definite order. Okay, so permutation, order matters. Okay, order matters. And so if we have A, B, and C, okay, let's just say we have 3 children, okay, lining up for water. Well, we could do ABC, we could do ACB. That's a different permutation. Okay? We could have BAC, we could have BCA. None of these are the exact same order, right? And of course, if we start off with C, we could do this, right? So these are 6 different arrangements, also called now 6 different permutations. Any questions on that? Okay. So permutations, a definite order of different items. Okay. All right. You could see, and I won't maybe go too far here, but if we had 3 things, but 2 of them were totally identical in every way, do you see a difference between this right here? No, not if B and B are identical. So when we talk about distinguishable, there's a certain way we're going to figure out the number of permutations. If there's identical objects, that's going to change how we figure out the number, because there's going to be fewer, right? So let's say we've replaced these, they've exchanged, but we don't. It's not different. So that's coming later, okay? So don't worry about that for now. But that's why distinguishable is important. Okay. So fundamental counting principle. Let's go back to that example in the text. Okay. So this one right here. Okay. There's one of the little girls there, and they're lining up the water fountain. So we could do this through the fundamental counting principle, couldn't we? So for that example, we have 6 children, and the question is, how many permutations do we have for them to line up, right? And what we could do is the fundamental counting principle. You say, okay, well, here's the water fountain over here. Okay, there's the water fountain. It's spraying some water there. And there are 6 kids. There's 1, 2, I'm not going to even draw stick people because it takes too long. 2, 3, 4, 5, 6, okay? So there's the 6 kids. There you go. That's just their faces, maybe. Okay. All right. They're all happy. And this person is super happy because, she's the front line. Anyway, so we have 6 kids, and so that means for each spot, there's a certain number of kids that could fill that spot. Now, on any given day, any of the 6 kids could be first, right? And then how many choices do we have for the second spot now? How many different kids could fill this second spot? Thank you, 5, because of the 6, 1 is already in the first spot. See that? Okay, so now for the third spot, we've got the first 2 placed. The third spot, how many kids are left that could fill that spot? 4, good. And then how many are left after that? 3, and then 2, and then the poor kid doesn't even have a choice. You got the short straw kid, you get to go to the back of the line, okay? So, does everyone kind of see that? All right? There's 6 options for the first spot, but then once that's already taken, there's only 5 kids left. So we have 5 choices. Now, to get the number of permutations, fundamental counting principle says we just multiply. Okay? So, what is that? Go ahead and get on your calculator and do 6 times 5 times 4 times 3 times 2 times 1. Or maybe you could do that in your mind. I'm not really sure. If you could do that in your head, you could try, right? What's 6 times 5? 30. What's 30 times 4? 120. What's 120 times 3? 360. What's 360 times 2? 720. And of course times 1. 720. Did you get 720? All right. Okay, so look at that. That's pretty good. If you guys could do that in your head, that's pretty good. Now, if this situation changed, all right, and I had, if we had a full class of, let's say, 25 kids, okay, and we have same water fountain, okay, this is the grade, this is the grade 1 class. Now we've got the grade 5 class, and they're all lined up, right? I'll save you the time here, but okay, 25. So how could I find the number of permutations for the order in which these kids could line up? Does it make sense that we would do the exact same thing, right? And we would start off with, and it doesn't matter where you put the number, of course, but you'd have 25 kids could fill that first spot. Once that's taken, 4, 23, and so on, all the way until you get down to the last one, right? Okay. So now what we're thinking, and what you should be thinking is, I've got a collection of different objects, and I'm trying to find out how they could be arranged in a line. Okay? And the number of different arrangement is called permutations, and it looks like if I have, n number of different objects, in order to find the number of permutations, it looks like I take that number n and I multiply it by 1 less than n, and then 2 less than n, and then 3 less than n, all the way down until I get to 1. And so for these first 2, that's the pattern that I want you to notice. Okay? So, to find, you want to write this down, please? To find the number of permutations for n, and we're just going to give it a number n, and they use n in the textbook, so instead of x, I'm going to use n, of n different objects, use fundamental counting principle. I'm just going to abbreviate that for you, FCP. Or you can think of doing this. Take n and multiply it by n minus 1. Then multiply it by n minus 2. Because that's what we've done in these examples. And so on, 3. And then this is sort of the way you write this. You kind of write multiply by and then dot, dot, dot. So it means that pattern continues on. But then you write something like this until you get down to the number 3 times the number 2 times the number 1. So this is sort of fancy math notation for what we did in these first 2 examples. Okay? Don't let it fool you. I remember when I got to university, and the prof would talk, and then he he would just write n and all these brackets, and I know it's university. It was like calculus stuff, and I'm like, whoa, wait a minute, what are those? What does that actually mean again? It took me a while to process that. So when we do these examples, and you see this up here, you're like, yeah, I totally get that. But then if you see it written like this, you might get thrown off and say, okay, throw my hands up in the air. That's why I don't do math. All right, right there, that sucks. But really, you think about it, it's just the same as what we did up here. But this n can be any number that we start with, right? It can be the 6 kids lining up for the water fountain. And so this would make 6 minus 1 is times 5 times 4 times 3, right? All the way until, oh, we've already got 3, so then times 2 times 1. Okay? But it also works for 25. If you start up with 25, that may, oh boy, it's going away. If you start up with 25, then this is 24. Then 25 minus 2 is 23, and so on. 22, see? Until you get all the way down. So it means the exact same thing. All right? So just for those of you that maybe your blood pressure may be rising a little bit here, don't worry about this. That's exactly, you know what that means here now. Okay? All right. So the cool thing, though, about this is you don't have to, if you have 25 kids and you're trying to find the solution to this problem, you don't have to actually, literally, on your calculator, type in 25 times 24. Wait for my calculator here. Okay? Whoa. Quit. Clear. You don't have to do this. 25 times 24 times 23. Because you might go mental before you're done. Right? That's no good. So there is a shortcut. There's a shortcut. Now, is anyone interested in the shortcut, or do you all want to do the long version? You're not interested in the shortcut? Okay. Oh, you do want the shortcut. Okay, good. I was hoping someone would say I want the shortcut, because that's what I'm going to do next. Okay? So on your calculator, there's a function. There's an operation on your calculator, and it's a very exciting operation. Now, I'm serious. Like, this operation is so exciting that they have to put like this exclamation mark behind it. So you may see on your calculator some really exciting function with an exclamation mark. You see that? You see an exclamation? It's actually not an exclamation mark, but it looks like one. So let's see if I've got one on my calculator. You know, I don't think I have one on this graphing calculator, actually. I don't think I do, because this is just, silly, this calculator. Oh, I do! Look at that! Look at this. I got to find it in my menu, but it's right there. You see that? Okay? Now, you probably on your scientific calculators, and hopefully you all have one. You have one? Yeah. No. You can't go get it. Just wait till I'm done. But on your calculator, you'll have an exclamation mark, which actually is the factorial notation. Okay? So, this is factorial notation. And so the factorial operator on your calculator would be this. Either it's just an exclamation mark, or this, sorry, I gotta quit calling it exclamation mark now. The factorial notation, okay, you might have an n factorial, you might have an x factorial, I don't know what you have. But anyways, that means, guys, listen to this, that means this right here. So your calculator can do this. All you'd have to do for this example here, when we started with 25 kids lined up, all you have to do is this, 25 factorial. Yes! You put that in your calculator, okay? So none of that. Let's just get rid of that. That's no good. 20. Actually, let's start with something that we know already. 6. Let's do 6 factorial. Now I got to go hunting for this thing. 6 factorial. Bum, ba da ba. I know. Mind's blown. Right? Is that amazing? Yay, for shortcuts, right? Okay, so let's try the 25. 25. Now, do you think this number is going to be pretty big? Yeah, gee, do you think? Wow, let's see. Oh, wow. 1.55, look at this. On your calculator, you may have scientific notation. That's 1.55 times 10 to the 25. Or 1.5511 all the way. This decimal gets moved over 25 times. That's a pretty big number. Okay? So, that would be sort of like a punishment. If the class is really bad, the teacher will say, all right, I need to see every permutation lined up at the door right now. Don't stop until you're done. That'd be like a good year-long project is what that would be. Can you imagine? You guys are like, oh, well, it sucked. I'd be here a long time. Like all the way through my spare. Yeah, you'd be here a long time. Okay. Factorial, got it? So, fundamental counting principle now is a little bit easier. If we actually went back, let's go back. Here's the question from 4.1 that we did. Now, can you use factorial notation here? No, you can't. Why not? Because it doesn't look like the pattern, does it? You don't go all the way down to 1, right? So you can't use factorial notation for everything. But you'll find that there will be actually a lot of different things you could use. Okay, so let's say we had. Look at this question right here. Remember this one with the codes with the little lock, right? Okay, so let's say we had 10 dials, and each of them had 10 numbers on them, and we couldn't repeat numbers. That would be a situation where you'd say, okay, for the first dial, I could have 10 options. Then for the next dial, because I can't use that same number, I only have 9. And then you go all the way down, and that's a situation where you could just do 10 factorial, because it ends up to be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And I know that just changes your life once you know that. So if you had, oh no, it doesn't? Oh really? Oh sorry. Sorry. That was actually a joke. I didn't expect someone to disagree with me so vehemently. But anyways, I realized it didn't stand. Sorry. Yeah, sorry. Just trying to make a joke here. Okay. All right. Now, I'm going to do a couple examples here using factorial notation. All right. So let's try and evaluate this right here. So write this down. 12 factorial divided by 9 factorial times 3 factorial. I know. Whoa. Okay. So here's a question. Now you know what this means, right? If we were to write this all out, that's 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, you know what that is. The bottom here, we've got 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And then we've got 3 times 2 times 1. Okay? So just do me a favor and write this out. Write that out. I know it'll take you a whole 7.5 seconds. Just write that out because this is important. I want you to see something here. And if you look at this, I bet you some of you, and I wrote this a certain way so that it would be easier for you guys to see something. Does anyone see what's going on here? Does anyone see how there's a shortcut to maybe simplifying this instead of punching that all into your calculator? Does anyone see anything that you could maybe do there? Okay, you can cancel the 9 to 1 on both sides, or on the top and on the bottom. That's awesome. That is exactly true. Now notice that this 9 factorial, right? That's actually 9 factorial right there. Those are all multiplied together, so we can literally divide those out with any common factors on the bottom. And of course, this is 9 factorial too. So yeah, that goes with that. They just divide out to make 1 over 1. It's like they're gone. And so all we have left is this right here. 12 times 11 times 10 divided by 6. So that's pretty easy, right? What you want to do is you kind of want to notice some patterns to make life a little bit easier for yourself. And so if you don't know what 12 times 11 times 10 is, okay, that's no problem. You can go ahead in your calculator. It's not a sin. Okay, 1,320 divided by 6, right? 3 times 2 times 1. If you have to do this on your calculator, I'm afraid that is bad. Yes. Okay. You will be punished severely for that one. But anyway, so you got 220. Okay? So that makes sense. Now, everyone get that? Everyone see how you can sort of simplify this and use the properties of what this actually means? Okay. I'm going to give you an example. It's a bit tougher, and there's definitely some sort of mathematic, symbolism and jargon in here, which may mess you up. But I think if you're exposed to it now, it shouldn't be too bad. So let's do let's do these examples on page 241. Okay? Okay, so I'm asking you to simplify. Okay, simplify. Now it says n is an element of natural numbers, so that just means we're just dealing with n values kind of from 1 all the way up and just positive integers, okay? So that's what we've been dealing with the whole time. There's nothing new here. So simplify. And I think actually there's this I've missed. Okay, factorial sign right there. Now this right here, if you take a look at this, you think, oh my goodness, what are we going to do? How do I simplify n plus 2 factorial? Well, that is going to be a bit of an issue, okay, if you write it all out, because you don't know what n is. So now you have to think algebra. And you have to think, okay, this is n factorial, and I'm multiplying that by n plus 3. Now, we're used to n minus 1, n minus 2, n minus 3. Okay, so this is what I'm going to suggest. N plus 3 times n plus 2. What would be next in this factorial? If we subtract 1 from this. So what would be next if I would just start to write out all this factorial stuff? So we have n plus 3, and then we have n plus 2. We should have n plus 1, right? And what's next? If we take 1 away from this, what's next? N. Okay. And then after that, of course, now we get into n minus 1, n minus 2, and that looks pretty familiar, right? And so really, what's happening is this goes all the way down until we get to 1. All the way until we get to the very end, which is like this, really, right? Does everyone see that so far? So if you take a look at this as a whole, what is that? What's a way we could simplify that? You could write that as one big package, okay? Where are we starting? We're starting with this number that is represented by n plus 3. And we're multiplying by each consecutive integer that's 1 less than it. So isn't this really n plus 3 factorial? You see? Okay? So you may not be there yet, okay, with recognizing these patterns, but really this can be simplified. You say, well, n plus 2 factorial, and then I've got one that's greater than, hey, this is actually the exact same as n plus 3 factorial, because n plus 2 factorial is in n plus 3 factorial. So that's just a part of it. Okay? Now, does that knock anyone off the cart here? Are you now not with me anymore? Is that tough, or does that make sense? Okay, getting into a little bit of algebra stuff here. Let me do one more example. Okay, one more example here. Again, it's a similar sort of example, but this one looks really tough at the beginning. Okay, so now we're dividing factorial expressions. And I lied. I think I need to do another example after this with you, but whatever. Okay, so you can obviously, I'm recording this for you, so you can look back and look at these examples again, watch them again if you need to. But if we understand factorial, what we understand is that this n plus 1 factorial is actually n plus 1, and then I'd subtract 1 from this, so that's just n times n minus 1 times n minus 2, and so on. So that's the same as this going all the way down to 1, right? And the bottom one, if I consider that, well, that's n times n minus 1 times n minus 2, and that goes all the way down to 3 times 2 times 1 until we get to 1, however many terms that is. So if you look at this right here, it's like, wow, what do I do? And please don't do this, okay? Here's just a warning message from Mr. Maxwell, please. Don't do this. Oh, there's an N, there's an N, there's an exclamation mark, there's an exclamation mark, there's a 1, there's a 1. The answer is plus over minus. Please don't do that. That is not correct. If you do that, I will die a slow and painful death, okay? Thinking my life is just worthless. So, yeah, now you're considering it. Hey, no. Oh, he's going to die a slow and painful death. I'm totally going to do that on my test. See if he shows up the next day. Yeah, you guys are a bunch of jerks. Okay, but anyways. All right. So don't do this silliness, right? Don't do that silliness, okay? And I'll try and get rid of those blues here. Okay. But what I want you to do is recognize that this is what's happening. Look at this. N minus 1 factorial and n minus 1 factorial on the bottom. See that? So just like we had that example before where you noticed that there was a bunch of factors that were the same, this turns out to be n plus 1 times n. That's all that's left. And it's in the numerator. It's up top. So you don't have to write over 1 or anything. And if you were to simplify this, you would go n squared plus n. Okay? So simplifying factorial expressions and factorial rationals. All right. Now, this is big time math, you guys. I'm going to tell you, this is a step up. So if you guys are with me so far, that's great. Okay? If you're with me, that's great. I'm going to give you one more example. Again, sort of, I guess this is sort of the third level example here. And so let's do this one. This one is example 4 in your text. So you can actually take a look at that if you want. And let's see, here's the text. So let's go example 4. Okay, so it's this one right here. And if you want to follow along, I may not show everything exactly like this, but I'm going to work through this question and solution with you. All right? And it includes doing some algebra, some quadratic equation solving. So depending on, how comfortable you are with that, we'll see how this goes. All right, so it looks like this. N factorial over n minus 2 factorial equals 90. And what we're actually asking for here is to solve for n. Okay? So now it's not just simplifying, now it's solving. So we have to find out what n is. But the good part is that we take a look at this side of the equation, and just like in the previous example, there's a way that you can simplify that. So that's what you want to do. You want to try and simplify this first. So let's see. You might be able to go straight to this point, but I'm just gonna show this. Okay, n. This is n. N factorial is n times n minus 1 times n minus 2, and then all the way the rest down to 1. And of course, on the bottom, you have n minus 2 factorial, don't you? And so I'm starting to just kind of tear this equation apart a little bit, and I'm saying, okay, this does not look very much fun to me. I don't know how to do this. How do I get n out of there? Well, what you do is you use what you know about factorial, and you start to rewrite it a bit. And this should emerge. You should start to see this and say, hey, guess what? This and this are the same on the top and bottom, and so I'm going to divide those out. And you're going to be left with an equation that looks like this. N times n minus 1 equals 90. And that's going to be a little bit easier to deal with. A little bit easier. So if we multiply that out, this is what we get. And that's going to be a quadratic equation if you do this. Now, do you see how we have a quadratic here, n squared, n constant term, and then it equals 0. It equals 0. So this is good stuff. This can be done. And again, I'm not sure how much you remember or how good you are at doing this, but we can solve quadratic equations. And one of the ways, if they equal 0, you can factor that trinomial, and then look at the factors will give you the indications for the answers. So there's going to be maybe 2 answers here. All right? So n squared minus n minus 90. So what you need to do, and we did this in grade 10, for sure. So you have seen this before, but what number multiplies to negative 90 and adds up to negative 1? So you want to think about the factors of 90. The first one that comes to me is 9 and 10. right? 9 and 10. That's a factor of 90. Now, one of them has to be negative because it's negative 90. So which one should I make negative so that they add up to negative 1? The 10? So 9 times negative 10 is negative 90. Check. 9 plus negative 10 is negative 1. Also check. So we do this. Plus 9 minus 10. And if you recall, how now we solve for n is, in this situation, right, this times this has to equal 0. So if that's the case, then 1 or both of these factors must be 0, right? So we have to kind of see what n values would make this 0. So you go n plus 9 equals 0. Well, what n gives us a 0 for this? Well, it's n equals negative 9. And the same thing over here. What n value? Well, n is 10 over here. So it appears that we have two answers. N equals negative 9 or positive 10. Okay? The only problem is that you're going to want to check these solutions. Because what happens sometimes when you do the quadratic, have quadratic equation, sometimes the answers you get, although they work algebraically, maybe don't work so well in the formula. So what you do is we're going to actually check this and replace each one of these numbers. Okay? So let's try 10 first, and we're going to have 10 factorial. So this is our check. 10 factorial over 10 minus 2 factorial equals 90. All right, so 10 minus 2, that's 8 factorial. So I've got 10 factorial over 8 factorial equals 90. If you remember, this is 10 times 9 times 8 factorial up top. Let me give me some space here. And this is 8 factorial on the bottom. And so those would cancel out. And 10 times 9 equals 90. That is true. Okay, that is true. If we check the other one, and what was the other one? Negative 9. So negative 9 factorial over negative 9 minus 2, negative 11 factorial equals 90. Remember that if we have a negative number and we subtract 1 from a negative number, we actually get a larger negative number. So do you see we have an issue here? That will never get down to 1. That's actually going away from 1. So same thing, if we have 11, negative 12, okay, times, I shouldn't put commas there, multiplying, negative 11. Now, does it make, negative 10, sorry, does it make sense that you could maybe do this? Yeah, if you're multiplying those, you could maybe do that. Is this going to get you 90? Well, that's going to go as well. What's negative 9 times negative 10? Mathematically, that is going to give you a positive 90, but what you have to remember is that n, when we're doing this factorial, n has to be an element of integers or natural, actually natural numbers, not integers, sorry. This only works when n is an integer, and n has to be a natural number. Let me just double check that. Look in your textbook there. Even though algebraically this works, the factorial notation only works for positive numbers, okay? So n is an element of natural numbers, which just starts at positive 1 and then goes up to 2 and 3 and so on, okay? All right, so that's sort of the toughest question that you will probably get in this section. So right away, if you have a negative number, you can stroke it off and say that's not it. The answer is n equals 10. Okay? Okay, so your assignment is 3 factorial, 580 and 8. Got it? I'm serious. Yeah, what do you mean am I serious? Yeah, I'm serious. He's like, no way, that's a lot of questions. No, it's actually just this right here. Right there. Okay? Not 3 times 2. Let's just do a list, okay? 3 and 2 and 1. Okay? Because you could think of this as 6 as well. 3 factorial. Yeah, maybe I should have done that. 3 factorial. No, that's the list of questions. That's 1, 2, and 3. Next time I'll do 3 factorial instead of the number 6. Just for you guys. See if you can figure it out.